Okay, welcome back for our last 5 presentation in the afternoon. So our first speaker is Luca Banatinik. His presentation title is Towards a Lubricated Wear Model Using the Finite Area Method. Okay, let's welcome.
So good afternoon, everyone. As mentioned, my name is Luca Banatinik, and for the next few minutes, I'm going to talk about the lubricated wear model using the finite area method. Using the finite area method. So we're going to talk about the implication of a wear model in some extent. Today, we're going to talk about dry, unlubricated sliding wear. But the rest of the research will focus on lubricated sliding wear, which I will present at the next time. So this presentation has 5 sections, and you can see them here. So tribology today, we can see a global shift towards clean and sustainable energy systems, and tribology has a pivotal role in achieving greater efficiency, meaning very stringent demands for lowering friction and wear, in electrification, meaning electric motors in which should be sealed when produced and should require no further maintenance, and in achieving better lubrication, meaning dry lubrication, new lubrication additives, or safe lubricating elements. So modern tribology has to deal with the minimization of friction and wear, with the reduction or complete elimination of any need for lubrication, with sustainable or biodegradable coatings and lubricants, and lastly, with the transition towards computational modeling. So we know that experimental tests are standard practice in various industries, for example, bearing design, but there are also time-demanding and costly trial and error-based methods which require real physical models. This is why numerical modeling emerged as a valid and cost-effective alternative to experimental methods in contact analysis. And with additional advancement of computational resources, greater accuracy may be achieved, allowing numerical methods to become a viable design tool or an add-on for existing tools, which is also capable of taking into account microscopic context and even friction. This is why assessing lubrication, friction, wear is very important, as those are crucial factors in, for example, bearing design. And if left unoptimized, they can result in lower productivity and even lower product quality. So this brings us to our research objective, which is to develop a numerical lubricated wear model, which can be used for wear analysis in numerical simulations of rotating machinery. This model is being developed as part of the finite volume method, or to be more precise, using the finite area method, which is a two-dimensional counterpart to the finite volume method. It needs to be applicable as a viable tool for wear analysis of lubricated rough surfaces, meaning that it needs to be able to take into account real surface roughness. And lastly, we want it to be applicable to numerical simulations of rotating machinery, which means initially we'll be using small test cases like ball and disc on pin on disc cases, and we will later on move on to larger cases such as turbo machinery examples or vane pumps. So our wear algorithm, which we'll use for simulations of surface wear, needs to be able to take into account real surface roughness, meaning real surface topographies. It should be applicable to dry contact conditions and different lubrication regimes. And lastly, it needs to be able to calculate both wear of the wear of single or both surfaces in contact. So there are 3 numerical models, which are the building blocks of the wear algorithm. First is the disparity contact model, then the lubrication model, and lastly, the wear model. The disparity contact model, together with the lubrication model or the fluid flow calculation, makes the lubricated contact model. And the lubricated contact model that we are using in this research has been developed and validated for wire rolling and drawing simulations by Mr. Skuric. Now, for conditions where there is no lubricant in the contact region, meaning for dry wear, we are only using a combination of the disparity contact model together with the wear model. Disparity contact models can be statistical or deterministic, and we are using a deterministic elastic perfectly plastic contact model based on the procedure proposed by Stanley and Cato and Salkin et al., which uses direct measurements of surface topography for calculating the necessary input variables, which are area ratios, contact pressures, and film thickness. Our sliding wear model is based on the arched wear model, where wear is modeled as the removal of lumps at contact areas, and it is also modeled as being proportional to the load. So the height of the worn volume, or wear depth, over a sliding distance L, can be calculated as given by the equations seen here. And the necessary input variables are the hardness of the software material, the dimensional wear coefficient, which can be determined experimentally for different pairs of materials, and lastly, normal contact pressure, which we can acquire from our contact model. So let's go through an overview of the wear algorithm. So initially, we start with the two surfaces in contact, their geometry and their properties. First, we need to resolve the initial contact for a predetermined load, which we resolve as the contact between the formable equivalent surface and a rigid plane, where the equivalent surface carries the properties of both surfaces in contact. Then, in each iteration, we calculate the combined wear depth, which is the wear depth for the equivalent surface, using the calculated contact pressure and the slight increment. After that, we can do the geometry update. So we use the combined wear depth to update the equivalent surface, or we use the dimensional wear coefficient belonging to each of the surfaces to calculate their contributions to the combined wear depth. And then we can repeat the same process. So we re-evaluate the contact, calculate the wear, and lastly, update the geometries. This we can repeat until total sliding distance is reached. Now I would like to move on to some validation cases. So first we'll start with the pin on disk sliding wear case. Here our results were validated against numerical data presented by the authors shown here. In our case, we have a pin with a 50 millimeter radius sliding on a rotating disk with a predetermined load of 10.2 Newton, friction being neglected. The material properties you can see here on the slide, and another important thing is the contact zone. So the contact zone is far away from the center of rotation, so it can be considered a square. Also, the dimensions of the contact zone are 1.2 by 1.2 millimeters, which is approximately 2 times the Hertzian contact diameter. There are two sets of cases I want to discuss. First, when only the pin is worn, and the second pair of cases is when both the pin and the disk are worn. On your right-hand side, you can see a schematic showing the contact between the pin and the disk, and the other image shows the contact zone, the contact domain we are using. So let's move on to the results for single surface wear. Here, only the pin is worn, meaning that the disk is considered sufficiently harder so that it does not wear. Initially, we discretized the domain using 32 by 32 finite area faces, as this comes close to the number of elements that were used by the authors I mentioned. And then we increased the finite area mesh to see how the results will change. The images below show the evolution of the contact pressure across the radial distance for different sliding distances. So here, starting with the 32 finite area faces, we can see that we have good agreement with the data from the literature. And for larger total sliding distances, we are closer to the data from the literature. But as we increase the mesh density, we actually consider that we are closer to the actual pressure distribution. Here, we decided to continue with the 64 by 64 finite area faces mesh. And for that, I would like to show you the single surface wear and the evolution of the upper surface profile for different sliding distances. On the left-hand side, you can see the 64 by 64 finite area faces mesh, for which we have excellent agreement with the data from the literature. And on your right-hand side, you can see that if we even use fewer faces or a larger number of faces, we still have excellent agreement. So for double surface wear, this is the case where both the pin and the disk are worn. The material properties are shown here. The geometry is the same. The mesh density is the same. On your left-hand side, you can see the case where both the dimensional coefficients of the pin and the disk, meaning upper and lower surface, are the same. And on the right-hand side, the same situation, but now the dimensional wear coefficient of the upper surface is 2 times greater than the one of the lower. We can see that the continuous lines show our results, the circles show the data from the literature, and we can see that we have very good agreement with the data from the literature. And on your right-hand side, as the upper surface has 2 times larger wear coefficient, the upper surface is worn more than the lower. Here, the same thing, but being visualized and using a scale factor of 30 for better visualization. The initial two images shown above are the initial position. The lower ones are the surfaces at the end of the numerical simulation. So let's move on to the next validation case. It's the ring on block case, where a ring is rotating while being pushed against a block with a predetermined load of 300 kilonewtons per meter. Here, only the block is worn, and the ring is considered sufficiently hardened in the disk. And the domain is discretized using 256 finite area faces along the contact width, because the initial contact is a line contact. So moving on to the results, on your left-hand side, you can see the evolution of the contact pressure, and on your right-hand side, you can see the evolution of the surface profile for different sliding distances. Again, our results compared with the numerical data from the authors given here. And I think that we have very good agreement with the data from the literature. Now, the same authors provided experimental data, and here we compared our numerical results to the experimental data that was provided in the literature. We can see that for the initial point after 75 meters of sliding distance, our numeric results show an underestimation of the width of the wear scar. The next 2 points show a slight overestimation of the maximum wear depth, but the initial reference point, for the end of the experiment after 300 meters, we have very good agreement between our data and the experimental data. Moving on to the last validation case, which is reciprocating motion of a ball sliding on a flat, which can be also represented as a periodic motion. Here, the initial stroke length was 2 millimeters, giving a constant average velocity of 0.1 meters per second. The domain, again, can be considered quadratic, with a contact zone discretized using 128 by 128 finite area faces, and the ball radius being 5 millimeters. Here, we can see again an evolution of the contact pressure for different time increments on your left-hand side, and on your right-hand side, the evolution of the worn surface of the ball. And again, I think that we have very good agreement with the numerical data provided by the authors shown here. With that, I would like to conclude. So for the conclusion, we talked about the development and validation of a VAIR algorithm in FOAM-Extend. We went through the building blocks of the VAIR algorithm. We said that it's made using a deterministic contact model, a VAIR model. We went through some validation cases, the pin-on-disc case, the ring-on-block, and ball-on-flat case. And to finally conclude, our current work needs some more validation, and we'd like to continue by using surface scans of real geometries with the deterministic contact model to show wear of real rough surfaces. And the last thing we are working on is the validation of some lubricated wear cases. So with that, I would like to thank you. Thank you for your attention, and please feel free to ask any questions.
Okay, very interesting. Any questions to the presentation? Okay.
Thank you. Question, maybe I missed part of the presentation. For the contact, have you used the penalty method or some other method?
We are using the method developed by Senekato, Sachen, and Altri. So it is using a deterministic contact model. And it is, as far as I know, it's not really based on the penalty method, or am I wrong here?
Thank you.
Okay, any questions?
Thank you for the talk. I have a very short question about the selection of the wear model. What is special about this model? Because you have mentioned this about the lubrication model, but you didn't mention anything why you choose this wear model.
Okay, I mentioned the lubrication model as being the next step in our research. The wear model used is the Archer wear model, and I chose this model because it is quite simple model which is being used for quite a lot of research, so I know that it is that it works and that I can find a lot of data using this model, so I can validate the results.
Thank you.
Okay. Any question? Okay. Thanks again for your very interesting talk.